want to apply, and then if you need to introduce additional unknowns, then you call into play additional conservation equation. So in general, when one builds a model, conservation of mass is the first law, and then other law follows if needed. And you can recognize, even in empirical models, this principle. The rational formula we identified, if you think a bit, that conservation of mass is implicitly imposed. Now, let me consider another Rainforth model. Now the treatment becomes a bit simpler, but the challenge is always to relate the basically empirical models that I am introducing with the physical laws. The next model that I am introducing was again introduced as an empirical model, more or less empirical. But we can call it conceptual, because you will see that in the empirical description people tried to identify the basic concepts of the Rainforth transformation. And let me introduce this model, which is called the time area method, again described in my slides. And a key feature, a key definition for the time area method is the definition of the time of concentration, or concentration time, which I already defined to you. I said the maximum time allowed to a drop of water wherever it rains over the basin to reach the closure. And of course you can understand that if a drop of water takes a longer time to reach the closure, it means that probably it rained much far from the closure itself. And let's moreover say that this concept of time of concentration is purely empirical. It has a physical definition, the maximum time taken by a drop of water. But if you really look at the physics, you may easily understand that this maximum time is impossible to define, because a drop of water could infiltrate and take even 20, 30 years to get to the closure. Therefore, you have to refer not to subsurface flows, you have to refer to surface flows. And this is implicit in the definition of time of concentration. And this is known. Some people in science, some researchers already pointed out that the definition as it is given is incomplete. So let's assume implicitly that we talk about surface runoff. And let's assume in principle that this time can be computed. So the time required to the drop of water, wherever in the catchment, to reach the closure, let's assume that it can be computed. And so let's refer to a catchment, and let's assume that we can, for a drop of water which is rained, for instance here, we can compute the timing. And a typical way of doing that is basing on expert knowledge to fix a uniform velocity of the drops to flow over the catchment. And then if you take a uniform velocity, then you can compute the time, the travel time. It is called, I didn't define the word soon, travel time, and the maximum of the travel time is the time of concentration. So you can compute the travel time if you assume a uniform velocity v, then you can compute the travel time as L divided by V, where L is the distance along the river network from the considered point in the catchment and the closure. So if you assume that, again, the drops have the same velocity, the drops, let's say the water over the catchment, surface water flowing over the catchment, has the same velocity V in all the catchment, then if you divide the distance between the considered point by the velocity, then you get the time, the travel time. Then if you make this assumption, it's very easy to compute the travel time over the catchment. And then you can easily draw over the catchment the isolines of travel time, which are called isochron lines, right? Like this. This may be 1 hour, this may be 2 hours, this may be 3 hours, and this may be 4 hours. Where 4 hours is, in this example, the time of concentration of the catchment. Let's say that from a practical point of view, it's not so easy to compute these isochrons, but from a conceptual point of view, it's quite easy. We just need a geographical information system with the river network overlaid, and then we can compute the distances for each point in the catchment to the closure, and then the travel times for each point. And then, once that for each point you have the travel times, you can draw the isochrons. Okay, now let's suppose that over this catchment rains for 1 hour. So we have a hyetograph like this. This is rainfall intensity, IT, and this is T. And let's suppose that if this is 1 hour, we have this rainfall. And let's suppose that the rainfall is constant for 1 hour. So let's put us in a simplified situation. And let's also indicate these areas between two subsequent isochrons. Let's indicate them A1, A2, A3, A4, where the summation of AE is equal to the total area of the catchment. Now, let's introduce another assumption. So far what we assumed, what did we assume? We assumed that we were able to draw the isochrons. We had the isochrons available. And this is not an assumption, sorry. Let's say that we refer to a situation where the isochrons were available and also the individual areas between isochrons were available. Now let's assume that the runoff formation at the closure, the river flow formation at the closure, is given by simple transfer of mass of water from the point where it rained to the closure. So the assumption is that the river discharge to the closure is formed by mass transfer, water transfer from the point where it rained to the closure itself. Namely, what is the concept, the very simple concept? The concept is that if I am capable of computing for each drop of rain the travel time, then I can compute how much water reaches the closure at any time. Okay, when we start with the hydrograph, we have basically the basin that is at time 0 is dry, starts raining, these drops land here and there, and then they take some time to get here. So if I know the time that they take to get here, it means that at any time I can estimate the river discharge here. And so the first assumption that I made is that runoff formation is due to mass transfer. Simple mass transfer. Second assumption, let's refer to a rainfall which is constant in intensity and is 1 hour long. And third assumption, this is very important, I didn't mention it, the rainfall is uniform over the basin area, over the catchment area, uniform. So what would be Q1, which is the river flow at the closure after 1 hour? What would it be? Now let's think of the process. Starts raining, you have the drops that fall here that immediately go to the closure. And this small area that immediately goes to the closure continues to contribute because it continues raining. After 1 hour, you have all this area here which is contributing. Do you understand why? Because after 1 hour, the drops started falling here, reached the closure, and all other areas are still contributing. So after 1 hour, we have a river flow, which is given by the runoff coefficient, which is always present to compute for losses, times rainfall intensity. Let's call it I1, because it refers to the first hour, times A1. So if I want to draw a graph of the hydrograph, time, after 1 hour, we are here, where this is I1, A1 times C. After 1 hour, we are here. You may ask me, what is the progress between 0 and this value at the end of 1 hour? Given that you have constant rainfall in time, the progress is, if you have constant rainfall in time, depends on the progress of the contributing area on time to get to 1 hour. If it is linear, then here you have a linear connection, meaning that if the area that contributes to the closure, to the runoff formation of the closures, increases linearly for increasing time, then the increase of discharge is linear. What does it mean if the increase of the area is linear? Very simple. You may draw a curve of the contributing area, which depends on time, depending on time. And we know that after 1 hour, if this is 1 hour, after 1 hour we get a value equal to A1. But of course, I didn't specify so far how we get to this value, if the increase is linear or non-linear. Now, it's very simple solution is to take a linear increase. If you have a linear increase, and of course, this depends on the shape of the catchment. If you have a linear increase, then you get, it means that the time area curve is linear, and also the other hydrograph becomes linear. Okay, now, what happens in the second hour? After 1 hour, it stops raining. So what happens in the second hour? First of all, let's consider what happens when it stops raining in general. Stops raining, you have the area A1, which is contributing after 1 hour, that stops contributing after 1 more hour. Because of course, after 1 hour, you have the last drop of rain that falls here. It takes 1 hour to get to the closure. So it means that after 1 more hour, after 2 hours, A1 is completely dried. So if we want to describe the hydrograph of A1 only, this would go to 0 to 2 hours. I put a dot line, not a continuous line, because this refers to A1 only, but after 1 hour, when it stops raining, we have A2, which is starting to contribute. So, after 2 hours, when the contribution of A1 is finished, after 2 hours, how much is the river flow? After 2 hours, we have A2, the area A2 that is contributing to the flow of the erosion. So basically we can write that Q2 is equal to C, again, E1, A2, which is something that may be here. If A1 is equal to A2, it's here. If A2 is greater than A1, maybe here, for instance. And, sorry, I should have drawn the line here, not there. Then you may have this situation. Now let me assume that A1 equal A2 equal AN. If you make this assumption, here the hydrograph remains constant until the second hour. So let's say that this is a possibility, which is under this assumption of A1 equal to A2 equal to AN is doesn't happen. So what happens in the third hour? Same thing. I have A3 that is contributing. So again, if this is the third hour, constant hydrograph. And again for the fourth hour. And then finally, you get a decrease of the hydrograph to the fifth hour. So the base time of the hydrograph is concentration time plus rainfall time. Is it clear how it works for you? I hope so. Now let's make another example. Let's assume that the rainfall duration is 4 hours, like the concentration time. Constant rainfall intensity, uniform rainfall, but 4 hours of rainfall. And now let's drive another hydrograph. Okay, so another hydrograph. Q, B, depending on t. And here I have 0, 1 hour, 2 hours, 3, 4, 5, etc. Now, at the beginning it doesn't change anything. So again, I have the first hour where the river flow is given by I1 times C times A1. At the beginning it doesn't change anything. But in the second hour, in the second hour, while the second area starts contributing, you still have the first area which is contributing, because rainfall didn't stop. Therefore, you don't have this dashed decrease of the hydrograph of the first area. You have the first area which is still contributing, and the second which starts to contribute. So, at the end of the second area, you have a river flow which is given by C A1, which multiplies A1 plus A2. Okay, so let's continue until the fourth hour. At the fourth hour, you have a river flow which is C A1 times A. C E1 times A. A is the total area of the catchment, and this is your then you have the decrease. The hydrograph is symmetric because rainfall lasted for 4 hours, and you get to 0 for a time that is again equal to concentration time plus rainfall time, which means 8 hours. Now, let me make a third case very simple. Let's suppose that rainfall continues for more than 4 hours, let's say 6. Then, when you get to this value of the river flow, which is C times I1 times A, you don't have any more increase of contributing area, because you have all the catchment that is contributing, which means that your hydrograph remains constant until the end of the rainfall, 6 hours. So you have your hydrograph that remains constant and then goes down and goes to 0 at 10 hours. Rainfall time plus concentration time. Now, let me make the final example. Let's suppose that rainfall is not uniform in time. Intensity varies from hour to hour. Okay. So let me write now in the form of a table how much is Q1. Q1 is given by the product C A1, sorry, I1 A1. Okay. Now let's suppose that in the second hour you have a change in rainfall, which becomes I2. Now, what is the amount of river flow in the second hour? Is again C, and then you have I1 A2 plus C I2 A3. 1. Why that? Because the second area is contributing the rainfall intensity that rained 2 hours ago, and therefore A1. While the first area is contributing with the current rainfall intensity, A2. Now, Q3 is equal to C I1A3 plus C I2A2 plus C I3A1, and so forth. We could write Qk as a summation for I equal 1 to k. We can generalize these equations in this way. C I A k minus I plus 1. Should work. Be careful, this is valid up to the concentration time. When you get the concentration time, these symbolisms are no more valid, because if it continues raining, you don't have any more increase in the contributing area, and therefore it becomes not valid. And let me say that if you want a more detailed description, you have to get to decreasing values of single a's. And then you may pass to an integral. The summation, if you go to infinitesimal values of interareas, then you can pass to an integral. And the integral is Qt is equal to C times, C is constant, so it can be brought out of the integral sign. It doesn't matter, just for simplicity. So C, integral between 0 and t of I tau, sorry, A t minus tau in the tau. Where AT is my time area curve, which I assumed to be linear. So if it's linear, this is TC, and this is. And this is A. So basically, this is the general formulation of the time area method, which says that you can obtain the river flow as an integral of the product between rainfall and the value of the time area curve. Be careful of the indexes. This is tau and this is t minus tau. Because you see here that one is increasing and the other is decreasing. Rainfall, the index for rainfall is increasing, the index for the area is decreasing. And sorry, I noticed a mistake. Just this is the derivative, not the product, but the derivative. The derivative. Because we don't want, we want the increment. If you remember to this discrete case, I was multiplying by AE, where AE is the increment. And therefore here, if I wanted to express this function by referring to the whole value, I have to pass to the increment with the derivative, which in the linear case is constant, by the way. Okay, now let me now make a couple of simple considerations. First of all, if you go back to the expression for the maximum river flow, for the peak flow, you see like here, you see that you get to a formulation that is the rational formula. So basically, the time area method, which was developed later than the rational formula, is a method that basically is a son of the rational formula. So it is based on the same consideration, and it gives back to you the rational formula indeed. And we will come back to this concept when we meet next time. Second consideration. Given that it's related to the rational formula, you can easily understand that there is a mass conservation principle here over the catchment. And in fact it is, because we assumed at the beginning that the river flow formation was due to mass transfer, which means that the mass is conserved. But there is one more consideration that is useful to make, because it allows us to better understand this model. There is another implicit conservation equation which is embedded in this model, very implicit. And basically, there is an assumption of conservation of energy or momentum, namely an assumption that it's implicit in the fact that you compute the travel time for a drop. The travel time depends on the energy which is available for moving. So basically, when you are computing a travel time, in whatever method you adopt, it's empirical, so you don't call energy into play, but implicitly, yes, you are calling energy into play. You are making an assumption on the movement, and therefore it means that you are using the conservation of energy. Or maybe conservation of momentum. You are free to choose one or the other. I don't want to insist in the details. Let's say conservation of energy. And now you may ask me, but why do I need this second equation? What is my second unknown besides the river flow? You may tell me you are wrong because we have just one unknown, so I can accept that you say that implicitly I am imposing conservation of mass, but you may say I don't accept that you tell me that we are implicitly imposing conservation of energy. What would be the second unknown? You may say I don't see any other unknown. Indeed, there is a second unknown, and it's important to notice that it exists because it allows us to better understand how the model works in practice. The second unknown is the volume of water that is stored in the catchment at any time. There is some water stored in the catchment. And there is some water because water takes some time to get to the closure. And in principle, with very simple calculations, you could estimate this unknown volume of water. You could do that because at any time you know how much water is rained and how much water flew out of the closure. Therefore, you could be able to estimate what is the water stored in the catchment. And this is the second unknown. And you can estimate it because you made an assumption of the travel time. This is almost philosophical, but I think it helps us to give some thoughts on how hydrological processes work. Okay, now, in 10 minutes, I want to introduce another model which is a bit simpler to introduce from a conceptual point of view. Maybe mathematically is not so simple, and you will be patient with me if I take 5 minutes more and if I hurry a bit to introduce two models. I want to introduce these two models together and not leave 3 weeks between the two, because they are strictly related and they are the basis for rainfall runoff modeling. So the beginning of rainfall runoff modeling was the time area method and the linear reservoir method. And I think the linear reservoir probably you already know, because it's used, the linear reservoir, in many applications, not only in hydrology. So again, please be patient with me a bit, so tomorrow you will be able to make the exercise by considering both models, and in particular the linear reservoir. And, you know, I prefer to introduce these two models close to each other. I don't want to leave 3 weeks. So I'm postponing some more consideration on the time area method and its relationship in particular with the rational formula to next time, for the sake of introducing the linear reservoir. And the linear reservoir makes reference again to our catchment, but makes different assumptions. For the time area method, the assumption was that the runoff formation is due to a mass transfer.